Hello and welcome to our online training for students presented by Dlubal Software. Today we'll be working with our FEA and design software RFEM, and the goal of this training is to go over the fundamental knowledge needed so students can model/work with any type of basic structure, view results, and understand fundamental basic theories. In this training we will be focusing mostly on simple models. My name is Alex Bacon, and I will be your trainer for today. I'm a technical support engineer, and am joined with my co-organizer, Amy Heilig, who is the CEO of the U.S. office, and a technical support and sales engineer, and we're located in Philadelphia, PA. Here's the control panel, and this will be used throughout the training. You can show or hide this panel as well as adjust audio settings. There's a box where you'll find some materials, and there's also a chat box where you can ask us questions as well. Please make sure this is set to organizers only. This training is intended for you to just listen, but you can model along if you would like. I can't stop and help you with any specific modeling issues, but with that said, feel free to stop and ask me questions at any time as I'm modeling about RFEM itself. Amy will interrupt me when she sees questions in the chat and as she sees fit, and then I can answer those for you. There will also be 2 breaks throughout this training. So today's training is from 1 to 4, and there will be a 5-minute break at 2 o'clock, and there will also be another 5-minute break around 3 o'clock. So just to go over the content for today's training, first we'll start off and go through the principles of finite element analysis software, or FEA software, and then we'll go through an introduction of our program RFEM. Then we'll go through an introduction example modeling continuous plates, and we'll go through some plate theory with that. Then we'll get into our model for stability analysis called Euler case 1. Then we'll model a moment frame, and with any time left, we'll model our concrete model, and somewhere in between there, I'll try to include some open discussion and questions if you have any. So that's it for today's content. Let's start with the basics of FEA software. So when using computer software, it is mostly based on the displacement method. Another method you may be aware of is the force method, where the unknown is the force, and then the internal forces can be calculated. With the displacement method, the unknown is the displacement, and to solve for this displacement, the displacement vectors must be calculated, and then the internal forces followed by the support reactions. The main problem today is an analytical solution can be difficult with large complicated structures. So doing hand calculations for some structures with complicated and/or odd geometry can almost feel and be impossible. The limits are being really reached with large complicated structures, and it's hard to get accurate results sometimes. And this is where FEA software comes in and helps. So with FEA software, first, the structures are modeled and converted into a finite interconnected element mesh. Then the material and cross-section properties are given at each FE node. And then the mechanical behavior is transferred between these elements. Here's a word that I would like to have you guys walk away with, and it's discretization. And basically this means structures being submeshed into finite elements. So now I'd like to go over the calculation workflow for FEA software. The first step that happens is the local element stiffness properties must be determined. And then those local stiffness properties are transferred to the global coordinate system. Next, the assembly of the entire structure takes place. And then the boundary conditions or supports must be defined. These can consist of, for example, sliding, rigid, or hinge supports. Next, the displacement vectors can be calculated by solving for the system of equations. And then lastly, the support forces and internal forces can be determined. So I just wanted to give a quick question, and that question is, what is discretization? And here are your options from A to C. And with questions throughout this training, you can just simply type the answer that you think it is into the chat, and then I can go over what the answer is and see what the majority of the answers you put in. All right, so I see some answers coming in. A couple people are saying C, some are saying A. I'll just give another 30 seconds to see if there's any more. All right, so it looks like it's pretty split between C and A. So for this question, what is discretization? The answer is A. It is a structure being converted into finite elements, and the other C, which is the other answer that a lot of people are saying, submeshing finite elements into smaller elements. I could see how that might be confused between structures converted into finite elements, but structures converted into finite elements is the correct answer. So now we can move on and get into our example. So here you can see we have a couple of continuous plates in this example. So we're going to model these plates in RFEM, and basically what we're going to do is compare the moment results with the continuous beam at the very end there and between these different continuous plates. So this should be pretty interesting. So now we can move away from the PowerPoint and we can jump into RFEM. So here's RFEM, and so what is RFEM is the question. I'm sure you all can guess that it's our FEA software, like I said in the beginning of the training. But just to specify, RFEM is a structural analysis software, FEA software capable of analyzing plates, members, and solids. So things like deformation, stresses, and internal forces can be calculated on a 3D first 3D structures. Almost anything is possible to analyze within RFEM, and specifically you can calculate things like deformations, internal forces, support reactions, and also things like volume of your structure and weight or mass. So just to go over the UI of this already modeled structure, this is just an example I have up just so we can go over the UI of RFEM. So basically, I'll turn my tables back on. So on the left-hand side here, we have our project navigator, and this panel is very useful and important in my opinion, and it includes all of the model data that you see graphically within what this is called your work window. Down here we have our tables, which is very similar to our project navigator, but the tables list out all of your model data in these tabs and in a tabular format, which allows you to pretty much change anything about your model data from nodes to lines to materials. You can input or delete anything you'd like. So this is very handy if you don't like working graphically on your model. Next thing I wanted to point out is the background. It is white. If you like to change the color of your background, I know some people have personal preferences when it comes to this. You can go up here to options and then configuration manager. And you can see right now I have my background set to white, but you can change this to black or some other presets that we have here if you'd like with this configuration manager. Next thing, this is the work window. And this is where I will be for the majority of this training working within this work window. I will go through tables and definitely use the project navigator just for examples for some things or some aspects of modeling. But for the majority of the time, the work window is where I will be working. The toolbar is what we have up here with all of our tools. Right now, it's organized based on the tool. And this, it kind of looks a little daunting right now with all the tools if this is the first time you've opened RFEM, but over time you'll find that it's easy to find the tool you're looking for. If toolbar does not look like if your toolbar does not look like my toolbar, then you can simply go up here and you can right click anywhere in this gray area and have this reset to default, and then all of these buttons will be reset to default and organized for you. Up here we have our insert menu where you can insert things like model data, loads, and load cases and combinations. There's also buttons in the toolbar for this. We also have our views up here that we can change through, so we can click through here on our buttons and change and go through our different views. Then within the project navigator, if I scroll down here, we have our long list of add-on modules, which I'll go over in more detail later on throughout this training. Next, we have our display tab. And within the project navigator, we have multiple tabs down here. One is called display. And you can see this has a similar design layout to the data tab. Basically, it uses collapsible and expanding folders that you can expand and change different things that are displayed within your model. For example, I can turn off my surfaces if I would like within my model using this. So lots of customization within this tab. And then we have our views tab. This allows us to change some views and change things within our model. So if we wanted to take a closer look at just our members by a certain material, if I just wanted to look at my members that are made of my steel A992 material, I can turn this visibility on and everything else about my model will be grayed out, allowing you to focus easier on some things and find some things better. And then the next tab is not here right now, which will be our results tab. So if I just run a simple deadload case real quick, I have my results tab that'll pop up. And within this results tab, we'll go over this in more detail later, just with everything else I'm explaining, but just briefly, this allows us to show which results we would like to see within our work window. So this allows us to change and go through deformations, member internal forces, surface internal forces, and strains, along with support reactions, sections, etc. So we'll go into more detail with that later. Next thing is how to move your structure around, how to control it. So right now I'm using a mouse with a scroll wheel. So I can simply just click my scroll wheel in and I can move it around. I can hold control and rotate my model. I can also zoom in and out with the scroll wheel. If you do not have a mouse with a scroll wheel, you can go up here to this button called Move, Zoom, and Rotate. So I can then just click and move my model around. I can hold Control and rotate, or I can hold Shift and zoom in and out. If you're using a trackpad, if you don't have a mouse, then you can use the keyboard and hold Control and use the arrow keys to rotate. You can use the arrow keys to go up and down, and then you can use the plus and minus buttons to zoom in and out. So now let's move on from explaining RFEM. I would just like to give another question real quick. So let's just hop back to the PowerPoint. So basically the question is, what is RFEM and then here are the answers to choose from. So again, you can enter those in the chat and we can go over the answers in about 30 seconds just and see what the majority of them are. Great, so it looks like mostly everyone is saying B, which is great because we can go through this. So what is RFEM? A 3D structural frame analysis program. B, 3D FEA program for calculating members, plates, and shells. Or C, a 3D FEA program only for calculating members. So I saw the majority of everyone answered B, which is great because B is correct. I would say some people said A. A is correct, but it's not, but it comes down to B being more correct. So RFEM is a 3D structural, A says 3D structural frame analysis program, but we can also, it's an FEA program, so we can calculate things like plates and shells and members. If we could only calculate frames, then it wouldn't be the 3D FEA program it is. So from that, we can move on and start modeling our continuous plates. So now we can hop back to RFEM. And we can begin by simply creating our new model. So to create a new model with an RFEM, there's a couple ways to do this. We can either go up to File and hit New, or we can simply just click on the New Model button here. And once we click on this New Model button, this box or dialog box will pop up called New Model General Data. And the first thing we want to do is fill out all of the information within this general data dialog box here. So I'm going to call this model or name it continuous plate or continuous plates. And then we can give a description. This isn't required, but I'm just going to call it, or just give it a description comparing plates and beam. And then we also have a function within RFEM, a project manager, where you can use this project manager to organize all of your models within a certain project folder. If you have a project with lots of different models and you don't want to have to keep saving them into a certain folder, this will do it for you. So it helps keep everything organized and keep your projects organized. Next, we have the type of model that we would like to set. So for this model, I'll keep it a 3D model. You can also create 2D models within the 3 different planes if you'd like. And then next thing is the classification of load cases and combinations. For this model, we really don't have to worry about creating load combinations automatically based on a standard, but I will just keep this checked anyways. But you can see here, according to standard, we have a long list of different standards from the ASCE to the Canadian standards, Eurocode, and some other ones as well. Next, we can change the orientation of our global z-axes. So I'll keep it as upward, but we can also change by clicking on this button, the local axis system as well, and I'll keep that as downward. And with all that given, we can click OK.
Hey, Alex, we have a quick question.
Mm-hmm.
The question is RFEM only an analysis program or does it also do design?
Yeah, so RFEM does analysis, basic analysis, like I said, the deformations, internal forces, etc. But we do design, and that's where our add-on modules come in. So our add-on modules do design based on material and standards. So that is something that we do have. So yes.
Thanks.
Mm-hmm. Yeah, so we can get into modeling our continuous plates. You can see right now we have our grid, which is blank right now. And this grid by default is 50 by 50 grid points here. And each one of these grid points is spaced 1 foot by 1 foot. And we can change this grid if we would like to, the settings of it, by going up here to settings of work plane. If I click on this button, I can change this. So you can see here, number of grid points. It's 50 by 50 in the negative and positive and X and Y directions. And then the spacing here is 1 foot by 1 foot. So this is great to have. We also have, you can change the amount of grid points dynamically according to your size of your model if you'd like. Also, another thing I wanted to point out before we started was that if you work in metric, right now for this training, I'll be working in imperial units, but just know that if you want to change your units at any time, you can go up here to options, units and decimals. So if I click on that, you'll see that right now I'm in imperial units and I can change any of my units for any aspect of my modeling, loading results and such. And I can also go down here to this button that says load saved profile. So if I click on that, I can double click on metric and I can change my units to metric if I'd like. I can also set metric as default. But like I said, for this training, I'll keep them in imperial. But just know you can change those at any time throughout your modeling.
Hey, Alex, another quick
Yeah.
question, maybe before we
Mm-hmm.
get into it that you can address. We
Mm-hmm.
have a question if it's possible to import in a DXF or DWG file in order to create the model.
Mm-hmm. Yeah, so great question. You can do that. So the way to do that would be to go up here to File, and then we can import different file types. So if I go to File Import, you do have the option to import DXF files in DWG files from CAD or AutoCAD. So you can see we have a lot of different formats and types here. So here we have the DXF file import, and we can also do direct imports through Autodesk and AutoCAD. So, yep.
Yeah, I think that explains it. Just to
Mhm.
further clarify on that, DXF file import is possible. DWG must be converted to a DXF in order to import. This would mostly be used for maybe a background layer to snap to the different points or to import in line elements. The direct integration that Alex mentioned will allow you to actually import in members and 3D faces into the program, and as long as the materials and cross sections match between the two programs, then the file or the model will automatically be generated with those member and surface elements. So that's the difference between those two options.
Yeah, that's right. Thank you for that clarification, Amy.
Yep,
Awesome.
go
Yeah.
ahead.
Okay.
Thanks.
Thank you. Yep, you're welcome. All right. Awesome. Yeah. Thanks for the question and clarification. So yeah, so let's get into creating these continuous plates. So first thing I'm going to do is create a rectangular surface on our grid here, and that surface will be 32 feet by 16 feet. So if I go up here to my new rectangular surface, and once I click on that new rectangular surface button, this dialog box will pop up, and all we have to do is tell it which material we'd like to make this surface out of and the thickness of it. So right now you can see I don't have any material defined. It's saying to create a new material. So what I can do is import a new material from our material library. We also have the option to create a new material if you'd like, but I'll click on our material library, and then you'll see our material library will pop up, and you can filter on the left-hand side here. So we have a material category group. I'm going to pick concrete. You can also see we have metal, timber, glass, and some other options as well. Then I'm going to pick normal concrete. And for this training, I'm just going to use the ACI, American Concrete Standard. But you can also see we have a list of other standards as well to choose from. And then I'm going to pick the latest standard, and I'm going to use 4,000 PSI concrete for the material. You can see down here we have our material properties listed, so always great to see. I'll click OK. And then the thickness, I'm going to make the thickness of this plate 12 inches, and then I'm going to click OK. And once I click OK, you can see that my cursor has changed from a arrow to a reticle. So right now I just need to tell it the program where the first corner of my plate's going to start. So I'll select the origin to keep it simple. And then I'm going to draw out this plate, which will be 32 feet by 16 feet. So I'll draw that out. And then I'll left click and then right click to cancel out of that tool. You can right click or hit escape to cancel out of any of the tools. And then I'm just going to rotate this. And now we have our concrete plate drawn on our grid here. Next thing I'm going to do is to create the same plate again. So I can basically just make a copy of this plate. So I'm going to select or highlight the whole entire plate. And then I'm going to use my move and / or copy tool to make a copy of this plate. I'm going to type in 1 for the number of copies. And then I'm going to, I can either type in the displacement where I want this plate to go, in which direction, or I can also use this button where I can select 2 points graphically. So I'm going to click on the bottom left-hand corner here, and then I want my plates to be spaced out by 5 feet. So that will be right here. And then I'm going to click OK, and now you can see that I made a copy of this plate, and they're spaced out 5 feet, or I could have typed in 21 feet or 22 feet in the displacement and the Y direction. And then the next thing we want to do is to create our third plate. So I can either use the move / or copy tool again if I would like, or I can also just highlight this plate, and then I can hold Control, and I can take this node here, and I can just use this node, and it will simply drag my plate. I'll make sure it's 5 feet apart, and then you'll see that it made a copy of my plate after I dragged it, and that was because I was holding Control. And that's a pretty easy way to make copies of something with an RFM if you know exactly where to place it. So now the next thing I want to do is I'm going to go up here and turn my tables off just so we can get a better view of our model here. And I want to take all of these plates and then just simply drag this and place it directly in the center here of my origin. And now the next thing, since now that we have our 3 concrete plates here at a thickness of 12 inches, I'm going to create my continuous beam. So to do that, to create a new member with an RFM, we can either go up here to Insert, Model Data, and then we can go down here to Members. I can do it graphically. It's asking me if I want to do a single member or continuous. So we have a lot of different options here for our members. You can also just go up here to this button called New Single Member. So I'll click on that. And once I click on that, then I'll get this dialog box here, and then I can just fill out this information. So right now it's saying this will be a member 1. I can do a rotation of the member, but the first thing or the main thing I need to do is tell it which cross section I want and material. So since we don't have any defined here, I can simply, just like the plates, go here to my import from cross section library button. I can also create a new cross section if I would like. I'll click on import from cross section library. And then the cross section library will pop up. And you can see within our cross section library that we have it organized by rolled cross-sections, built-up cross-sections, parametric thin-walled, parametric massive, timber. You can also create user-defined sections like I mentioned. And for this example, I'm just going to go up here to parametric massive, since we're just going to be using a rectangular concrete section. And all I have to do is type in the dimensions of my cross-section. So our base is going to be 40 inches, and then the height is going to be 12 inches to resemble the thickness of our concrete plates that we've created. Then for our material, I'm going to keep it the same as the concrete plates as 4,000 PSI concrete. But you can also go into the material library here and tell the program which material you want your member to be. So once that's all filled out, I'm going to click OK. And now you can see that our cross section is here with our material, and this is the start of the cross section. And so I'm going to click OK again. And now I can simply graphically just draw my member anywhere on my grid here. One thing I forgot to mention was that your cursor does snap to these grid points here. So that's why changing the spacing of your grid points is kind of important, just so you can easily draw out your members if you do it graphically. So I'm going to place this member 5 feet from this upper plate here, and it's going to be the same length of our plate, so 32 feet long. And I'm going to left click, and now you can see that our member here has been drawn out. And now we have our plates and our continuous beam here.
Hi, Alex. We have a question. What is the
Yep.
difference between parametric and standard sections? So maybe you could explain parametric versus choosing a section from, let's say, one of the standards.
Yeah, so I will go back to the cross-section library to point that out. So basically, when it comes to standard sections, these sections are all based on a standard. So if I click on our rolled up sections here or our W beams, you can see that I choose a standard here, and these sections are basically based on a standard, and you can't really change the dimensions of these. And so that's what that is, or those are. And then if I cancel out of that and then go back to the cross-section library, the parametric sections, basically you can tell the program exactly what the dimensions of your cross-section will be. So if I click on a W section, you can see here that I can change the dimensions of my W section here, the thickness and the base, and that's what allows them to be parametric. And yeah, so just to clarify, the standard sections are based on a standard and can't really be changed with dimensions. And then the parametric sections, you can change or you have to input the dimensions of them.
Okay, thank you.
Yep, you're welcome. Yeah, so we created our continuous beam, and then now the next thing we want to do is to divide our lines here. So what I want to do is add some line supports or a middle support to each of our spans here, to our beam and our plates. So to do that, I'm going to simply just divide our lines here. So if I wanted to divide a line, I can simply right click on the line, and then my shortcut menu will pop up here, and I can go up here to divide line, and you'll see you have a couple different options for dividing lines. You can either divide a line graphically, tell it how many nodes you need to place from the beginning and end of your line, or you can tell it to split at a certain distance. So for this line, for example, I'm going to divide it graphically, and I simply just want to divide it exactly in the middle. So I'll go to 16 feet or 16, and I'll left click. And so now it'll place this node and split both of these lines directly at that node. I'll right click, and then I'm going to do the same thing for this line up here. I'll right click, go to divide line graphically, and place a node here at node 16. And now both of my lines here are divided. And now I can simply draw a new line. So you can draw lines without having to have them create a member. So I'll just do that. I'm going to, oops, not sure how that happened. So what I can do is hit Control Z and undo that drawn line and go back. And then I can draw my line, and you can see its lines are snapping to the nodes here. Then I'll right click to exit out of that line. And then the next thing I'm going to do is to basically, instead of having to divide these lines here, I'm going to take this line that I just drew at the midspan, hold Control, and I'm going to drag it directly above. And then I'm going to do the same thing. I'll select this line, hold Control, and drag it to the next plate. I must not have hit Control before I dragged it, so let's try that again. There we go. So now we have all of our midspan lines here on our plates. And then the next thing I'm going to do is to divide my beam here. So I'm going to right click on it, and then I'm going to go up here to divide member. And this time I'm going to divide it by a distance. I could have done this graphically, but just for example purposes, if we choose to divide something by a distance, you can see this box will pop up, and I can choose the type of division, so divide line by intermediate node, or place a node on the line without dividing it. So we'll have it divide the actual line with the new intermediate node. And then the distance relative to, I want to do the whole member length. You can do projections in a certain direction or on a certain plane. And then basically I just want to divide this line at the very center, so 50%. You can also type in a length from the member start or member end. If you're confused about which direction the member has been drawn or the orientation of your member, you can see when this tool is open that we place black arrows on top of every member, and you can see that points the orientation of your member and tells you which side is the start and end of it. So since it's directly in the middle, I'll keep this at 50% and click OK. And now you can see my node has been placed and it divided our line here, or our member. And now we can place a support here if you'd like on this node, which we'll be doing in just a little bit. So the first thing I'm going to do is create a nodal support and a line support, and all of our supports basically for our plates here. So I'm going to go up here to our toolbar and go to new line support. So I'll click on that. And then you can see once I open once the new line support tool opens, that right now we have our default set to hinged. So our type of support is set to hinged. So if I hit this drop down box right here, you can see we can choose between two presets here. We can either choose from hinged or we can choose rigid. So you can see for hinged, this is what they look like. So basically we have our 6 degrees of freedom. These 3 right here are our translation degrees, and then the unchecked boxes are our rotation. So rotation is all released and all degrees of freedom. Translation is all fixed. And then something for rigid, we would have all of our translation and rotation degrees of freedom completely fixed. And you can see what those supports would look like here in the graphic. Just real quick, you can also create new types of line supports. They don't have to be just the presets. So if I open up new line support here, this box will pop up, and you can see we have our 6 degrees of freedom where you can check the box to fix it, or uncheck the box to have it be released. You can also add in spring constants, and we also have nonlinearity options for our supports as well. So for now, I'm going to just stick with rigid, or I'm sorry, hinged line supports, and I'll click OK. And once I click OK, you can see I have this little icon next to my cursor here where the program's saying, okay, which lines do you want to apply these line supports to? And basically, I'm just going to apply them to our end, middle, and start of our plates here. So now all of our line supports are added to our plates. I'm going to right click because now we want to add our nodal supports to our beam up here. So I'm going to go up here to new nodal support instead of new line support. And you'll see this looks basically the same as the line support tool, just nodal supports instead at point locations. Again, we have presets, including sliding in the X direction and sliding in the Y for your rolled supports. So I'll keep it as hinged for 2 of our supports. So I'll click OK. And basically, we'll have the end of our member here be a hinged support and the middle will be a hinged. But our last support here, we need to have it be defined differently. So I'm going to create a new support for our start of our member here. And this support is going to be a hinge support, but I'm going to fix rotation about the local x-axis here. And I'll click OK. And the reason I had to create this new support type is because if I would have made this whole member all hinge supports, then this member would have infinitely rotated about its local axes. And its local axes, I'll show you real quick. So I'll right click on the member and I'll turn our local axis system on for our members. And you can see this is our local axes. So we have our Z, Y, and X and lowercase. This is independent from our global axes. And we would have gotten an instability if we would have had all of the rotation released because it would have just spun about this x-axis. And so that is the reason why we had to create this independent support here to keep it from rotating. So now we can add the loading to our model here. And we can do this in various different ways within RFM. We can add our loading through the tables here. I can go to table 2, and I can also do it through the project navigator. But the first thing we need to do before we can add in our loads, which is very important, and that is to create a load case because every load needs to be assigned to a load case. So we need to open our load cases, or we can go up here to this button called Create New Load Case, which is what I'm going to click on. So this new load case box will pop up, and you can see it created a new load case already for me. And right now it's asking me for a load case description. I'm just going to name this load case test, and I'm going to keep the action category set to dead. And then the self weight, you can see, is automatically checked on for this load case. It's set to active. And the factor in the direction here, -1 in the Z direction, that's going to basically just give us our self weight, which is multiplied by the specific weight of our material and the volume of our structure. So that's how the self weight is taken into account. And if you create another load case, you can see that the self weight is not taken into account. So it's important that you only have the self weight active for one of your load cases. If you have it active for multiple load cases, then the self weight of your structure would be taken into account multiple times and you would get inaccurate results. So I'm going to delete this second load case, and we're only just going to stick with one load case for now, just to keep it simple. And we can now click OK. So now that we have our load case, we need to assign loads to this load case. And like I said, we can either do that in the tables here. I can add in nodal loads, member loads, line loads. You can see that that's all organized in the tables here. You can also see that our loading is organized in the project navigator as well. So if I wanted to add any of the loads here, I could do so. But I'm going to go up here and I'm going to click on a surface load because we want to add loading to our surfaces here. So I'm going to click on this button here called New Surface Load. And once I click on that, I need to go through this dialog box, and basically it's telling me the number of the load that's assigned to this load, and it's asking me what surface numbers is this load going to be on. You can see, well, you'll find out after once I fill this information out that we can just graphically assign the loading. So I want the load type of this load to be force, and I wanted the distribution of it to be a uniform distribution, so I'll keep that the same. And then I need to specify the direction. I want it to be in the global Z axis. And now I just need to tell it a magnitude. This is set in kips per square feet, or KSF. And I'm just going to have it be negative because I want it to go downwards, 0.210. So basically 210 pounds per square foot. I'll click OK. And now you can see my cursor has this icon next to it telling me I can select my surfaces that I want to apply the loading to. So I'm going to apply it to this first surface, the second one, and then the third one. And then I can right click and I can see my loading graphically now.
Alex, can you explain the difference if you double click on the surface load again?
Yep.
When we're looking at the two different, or I guess 3 different directions here, local axes versus true area versus the projected area.
Yeah. So basically when you're picking your direction, you have these 3 options. You can choose the local axes. So the local axes, you can see throughout RFEM will always be a lowercase letter telling you it's the local axes. And then we have a choice between global axes. So just to start off, the local axes is the local axes of our surface here. So if I exit out of that and turn off our loads real quick, I can right click on my surface and I can have it show the local axis system. And so basically, this is the local axes of our surfaces. So if I go back into, if I wanted to apply the load in the Y direction, that would be a different direction compared to the global axes. So if we go back into the loading here, you can see that I can choose between that. Also, if I choose the local axis here, you can see in this graphic, it'll show you the direction of your local axes on your surface if you're ever confused. So you don't really have to exit out of this panel to see that local axis, but I did just for visualization reasons. And then the difference between these two, the global related to true area and the global related to projected area. So if I do true area, right now my plates are flat within the XY plane. So my loading will be applied to the true area, or the exact, sorry, the exact area of our plates here. But if I choose projected area, and for some reason we have, let's say like a slanted roof or a roof that's slanted downwards, and we're applying, let's say, snow loads or something, we don't want to take into account the exact true area of our surface here. We want to have it projected in the Z direction, and that would be a lot less area compared to the actual true area of our plate here.
Yeah, I think that's good.
Yeah, okay. Hopefully that answers your question. So we'll stick with the true area, which I guess, for example, for this, it wouldn't really matter if we chose projected or the true area since it's completely flat. So we'll click OK. And now we have our loading placed on our plates here. 210 pounds per square foot. Now we just need to place the loading on our continuous beam here. And to do that, so I can turn off and I can show or hide the loading just for easier, just to be able to see it easier. I'm going to turn off the loading, or not, or hide it, I mean. So to place a uniform load on a member now instead of a surface, we have two different options, or we have one option. It would be a new member load. We also have this new line load tool, which is only for lines that are not members. So keep that in mind. For members, you always want to use member loads, and for line loads, you always want to use the line load tool. So we'll click on new member load, and then I'm going to go through this dialog box again. You can see it looks similar to the surface load dialog box. So the load type will be a force, and the load distribution will be uniform. You can see we have some different options here for that. We also have the load direction. So the global related to true member length, we're going to choose that one. Again, you can choose projected in the global direction, or you can choose the local axes. For load parameters, we're going to type in, for this member, we're going to keep the loading relatively the same to the loading on our plates. So that would be negative 200 and, well, 0.210 kips per feet. We'll click OK. And then we're going to apply this to our member and right click to exit out of the tool. And now we have our loading. Oops. We have our loading applied to all of our surfaces here, or our plates, and also to our continuous beam. So now the next thing we want to do is to create what is called an FE mesh refinement. So I'm going to hide the loading here. And basically for our FE mesh refinement, to create these, we can just simply right click on our surface here. And we
Hey,
can,
Alex, sorry to interrupt.
Yep, no
Maybe
problem.
one quick question before we go into the FE mesh.
Mhm.
Maybe you can quickly explain the difference of a line load versus a member load, as they almost look identical in the toolbar.
Mhm. Right, yeah. Yeah, so basically the line load, so I have my member here drawn, which is basically if I go into wireframe view, so I can change the rendering of our model here to wireframe. Basically all members are made up of lines. They just have a cross-section of material assigned to them. But you always want to use the member load tool to apply loading to a member, and you want to use the line load tool to apply loading to a line. So, right, this is a line defining our plate here. It has no cross-section or material assigned to it. It's just strictly a line. So let's say if I wanted to apply loading along the parameter of my plates, I would use the line load tool, and I would simply just type in magnitude, and then I could, oops, if I go back to the line load tool. So again, I could just simply use this tool to apply loading to the lines that make up the parameter of my plate here. They're not members, they're just lines. But if I wanted to, like I said, apply a load to a member that actually has a cross-section and material assigned to it, I would have to use I couldn't use just the line, new line load tool. I'd have to use the member tool, new member load tool.
Yeah, I think that an easy way to remember is member load should be applied to members, and line loads are applied to either surfaces or solids. Otherwise, the program will flag you with an error. So yeah, that should explain it. And just to let you know, on that third surface, you still have an existing line load that you'll want to delete.
Oh, yeah. Okay. Yeah. Thank you, Amy.
Yeah,
Yep.
sure.
So yeah.
Okay,
Yeah.
thank you.
Yep. You're welcome. Yeah. Great question. So I'm going to delete that. And then yeah, so now we have our loading, and yeah, the next thing we're going to do is add FE mesh refinements to these plates here. So just a quick overview for our FE mesh. Basically, the FE mesh in RFEM is automatically created when you run your calculation. There's a set length to your finite elements. By default, with imperial units, it's 1 foot by 1 foot. But let's say you wanted to change that mesh length for a certain element. Say these plates, you don't want them to be 1 foot by 1 foot. You want to change them to something smaller and more refined. You can use an FE mesh refinement and just change the finite element length on a certain plate. So I'm going to do that, and I'm going to add different FE mesh refinements to these plates. And I think this will it might be a little confusing right now, but I think it'll start to make sense once we move throughout the example. So I'm going to start with this plate. I'm going to click it. I'm going to right click on it, and then I can simply go up here to the option New FE Mesh Refinement, and I'm going to click on New. And it's saying that I don't have any FE Mesh refinements defined. So what I can do is create a new FE Mesh refinement. And then on the surface, it'll be an FE Mesh refinement applied to our surface here. And for this first surface, I'm going to have a super fine refinement. My target FE length is going to be 0.2 feet. So I'm going to click OK again. And you can see I have this little icon down here telling me that an FE mesh refinement is placed on the surface. And this little symbol here will show me also how large that FE mesh finite element will be. So then I'm going to do the same thing for this next surface. I'm going to add another FE mesh refinement to it. And I can choose that previously defined FE mesh refinement, but for this surface, I'm going to make it just a little bit bigger. So I'm going to create a new refinement, and I'm going to, for just example purposes, make the finite element length 0.4 feet. I'll click OK. And then the next surface, I'm going to right click, create a new FE mesh refinement, define a new FE mesh refinement, and I'm going to make it 0.6 feet, and then click OK. So now you can see we have our surfaces here with 3 different FE mesh refinements on them, and you can see that those elements get a little bit bigger from 0.2 feet to 0.4 feet to 0.6 feet. So you can see graphically the different sizes of those. And then the next thing we want to do is to create sections for these plates. So we can add in section cuts down or along the whole span of them, down the center. So to do that, we can easily just, I can rotate my model, and then I can go up here to this button, and I can hit this arrow drop down for different options within this tool. And I want to create these sections numerically. And I want to give my section a name. So I'm just going to name this first one AA. I wanted to cut through my surface, and I want it to be via plane. And then I just need to tell the program the first and second point to cut through. So I can do that here with my coordinates, A and B, or I can simply just click on select edge points. And then I'm going to choose the first point here, which you can see nicely, just like in AutoCAD, your cursor will snap to directly the midpoint. There's a little symbol there telling you it's the midpoint of that line. So I'm going to snap to that, and then I'm going to snap to the next point, which will be the end point. Then it's asking me to select the section on the surface or the projection. It's just going to be a vector, and it automatically does that for you once you select your edge points. And then the plane, it'll be in our local positive z-axis plane, and everything's filled out now, so I can click OK. And now you can see graphically we have these arrows here symbolizing that we have a section cut through our plate there. And now the next thing we can do, instead of having to go through all of those parameters again, is I can hold Control and use the pretty powerful workflow of just dragging and copying these section cuts to my other plates here. And now we have all of our section cuts here. Dragging and copying does give you some different nomenclature here, but we can easily change that within the project manager, or sorry, project navigator. And I can do so, I can just simply go up here to, or go down here to sections, the folder sections. I can expand that. And then I can just change the name of my sections real quick by double clicking and editing them. So I can just make this one AB. And then this third one, I can just make it AC. And I'll click OK. And now we have all of our section cuts here with our different names on them. And so now basically everything is ready to run our calculations. We have our supports, we have our plates here with our cross sections and areas with materials defined. We have our load case here, and we have our loading assigned to our load case. So now we can simply just go up here to calculate, and we can go to calculate, and then we can just simply choose our load case here, move it over. We can also run our load combinations and result combinations, which we will get into a little bit later. But for now, I'll just run this load case. I'll click OK, and it should start going through the calculation. So,
Hey, Alex, while that's running,
mhm,
we have a good question that was asked from an
mhm.
analysis point of view. What is the difference between an FE mesh refinement and simply splitting the surface?
Yeah, so from an analysis point of view, so if you split, basically splitting the surface really wouldn't change too much. It would just, yeah, I could split the surface and have these be two different surfaces, and or I could basically keep splitting them and have them be smaller and smaller, but no matter what, the FE mesh will stay the same length on the surface, whereas changing the actual FE mesh length will increase the accuracy, as results will be assigned to many more points along the length of your surface, if that makes sense.
Yeah, and I think that technically a user could take a surface and they could keep splitting it, just as you mentioned, into smaller and smaller surfaces.
Hmm.
And the program will adapt the FE mesh to accommodate all of these small surfaces so that maybe you only have an FE mesh element of 1 across the width of all these small surfaces. So this definitely could be an option instead of defining an FE mesh, as the program will
Hmm.
adapt to that. The problem is that now you're dealing with hundreds and hundreds of separate surfaces for your results interpretation,
Hmm.
whereas we would prefer to keep these surfaces as one continuous element and to internally submesh, and that way our results will be much simpler to read. So that's the suggested route rather than to manually keep splitting these surfaces into smaller elements for accurate analysis. Overall, you could get the same results, but one approach is much easier than the other.
Yeah, that's, yeah, actually, yeah, great question. I never actually really thought about that. So yeah, awesome. Yeah, great explanation, Amy. That makes sense. So I think now is a good time to take a break. So it's a little past 2 o'clock. We have our results ran, and so we can go over these results and continue going through our model here. I think we can come back here. We'll take a 5-minute break. So we'll come back here around 2:10 and we'll then resume. So. All right, so I think we can resume now. We can jump back to RFM. And what we mostly just finished up with was calculating our results. So now that everything's calculated, we ran our results for our load case 1 here. And you can see right now we are showing our global deformations of all 3 of our plates here. And also you can see this yellow line here is our deformation of our continuous beam here. And we're also showing the resultant of this deformation. So we can also go into our components here for our deformations. And we can also show the internal forces of our member here. So we can view our internal forces, we can view our moments about our y-axis, our local y-axis here. So we get a nice moment diagram graphically on top of our beam here. I can turn this back into our solid transparent render view, but it is easier to see the diagram here with just the wireframe view on. And then we can also take a look at our surface internal forces as well, or the results on our surface. So we can take a look at the moments along our x-axis here on our surface. And you can see also that these deformations on our surface and the internal forces are color-coded. So with that, we have our panel here that allows us to see the color-coded, or we can see what value is assigned to the color that is on top of our surface. Then we can also take a look at our support reactions as well. So we can turn our support reactions on and get a look at those. So we have a choice between our nodal supports and our line supports, and we can see which direction we want to see those reactions along with our moment reactions as well, if we would like to view those. And we can also activate our section. So I'm going to turn off these support reactions, and I'm just going to collapse some of these just so we can get a better view. So if I go down here and turn on our section cuts, I can get a nice view of our section. So now you can see the results, and you can also maybe now see the difference in accuracy between the plates that have different FE mesh refinements sizes, or refinements on them. And so now I think it's a good time to mention that the size you pick for your FE mesh affects your results. So you can go up here to calculate, and then we can go into the calculation parameters tab. And once I go into my calculation parameters tab here, I can go under the global calculation parameters tab at the top here. There's a couple other tabs, but we'll just focus on this global calculation parameters tab. And within this tab, we have lots of different options here, but I mostly just wanted to focus on the one option here. And this says activate shear stiffness of members. And basically, this is an important option because if you're trying to compare your hand calculations to RFM, RFM is always running calculations with the shear stiffness of members considered. And you can turn this off. And once this is done, you will have to recalculate your model. So if I click OK, I turn that option off. It's saying this action requires that all results will be deleted. Do you want to continue? You will always see this box come up even when you change anything within your model, such as cross sections, materials, dimensions. Results will be cleared, and it'll ask you to rerun them. So I'll click yes, and then I'll rerun my results. And once I rerun my results, you should notice that mostly the only results that really change from this are the bending moments. So right now I'm showing my moments, and if you're paying attention, you should see that the results or the maximum moments have changed a little bit at their peaks. You can see right now they're a little bit different because of the FE mesh sizes, and they changed from this option because the methods used in school mostly assume an infinite shear stiffness, when in reality there are some shear deformations happening when the member bends. So I'd just like to have you keep this in mind. So I'd just like to have you keep this in mind when comparing hand calculations of deformations with RFM. And this is something that you can change within the calculation parameters. And so also, just to go back to, so now I would like to go back to the PowerPoint so we can go over and compare some plate theories. So I'm going to turn it back over to the PowerPoint. And we can start with plate theory. So basically, to help you understand what's going on with plate theory, I will use beam element theories as an analogy. So basically, the first beam element theory is Bernoulli's theory, and then also the next one we have is the Timoshenko theory, and I will be comparing the two assumptions between these two theories, as they're both kind of similar but also different with one aspect mostly. So with Bernoulli's theory, we assume that cross sections remain in plane and perpendicular to the member axes, with the assumption that no consideration of shear deformations is happening and that the member is completely rigid, has completely rigid shear stiffness. Whereas with the Timoshenko theory, we make the same assumption basically, that the cross section remains in plane and perpendicular to the member axes, but we take into consideration shear deformations, and we assume that the shear stiffness is limited and it isn't completely rigid. So I have a graphic to represent what this means between these two theories. With Bernoulli's theory, here you can see the deformation is perpendicular to the member axes. But with the Timoshenko theory, here we have an additional angle that is incorporated. So we have basically a different additional deformation. And this is due to the assumption that the shear deformation or shear stiffness is not completely rigid. And we take shear stiffness into consideration. So taking these two theories, we can apply them to plates or to plate theory, as because they are a little bit similar. So an equivalent analogy for plate elements, we have the plate theory, Kirchhoff's plate theory, and then we have the Resner-Mindlin plate theory. So these are similar to the Bernoulli's and Timoshenko theory, and you will see why. So if we show the assumptions for the Kirchhoff theory, these can be compared to the beam theory. So these assumptions, basically, we assume for the Kirchhoff theory that we have very small deformations, and it's a geometrically linear calculation for the deformations. And then we assume the material is linear elastic using Hooke's law. We assume the cross sections for these plates remain flat with no warping. We have a constant thickness, and most importantly for this theory, we do not consider shear deformations. Now for the Resner-Mindlin theory, we assume basically the same assumptions for the Kirchhoff theory for these first four assumptions that I mentioned, but the difference is we do consider shear deformations, and we also take into consideration the transverse and lateral strains. And so to take a better look at what this assumption is talking about for transverse and lateral strains. I have a little bit of a graphic example here for transverse / lateral strain. So here we have a beam, and that also has a tension force applied to it. And this is along its length. And the cross section, if this tension force is here, will basically shrink with regards to its height and its width. And you can see here for its height and width that this mu factor here is what takes this consideration into account. And so that's how transverse / lateral strain is considered in the Resner / Midland theory. So just to recap for plate theory, Kirchhoff theory, Resner-Midland theory. For Kirchhoff theory, we do not consider shear deformation, so it's a little bit more of a simpler theory. It's kind of like Bernoulli's, where we also don't consider, for the beam theory, where we don't consider shear deformations. And this theory is great for thin plates. It's great for pure bending, load-bearing capacity type plates, and also it's a simplified approach. But for the Resner-Midland theory, the consideration of shear deformations is there. And this theory is great for thick plates because the thicker the plate gets, the less accurate your results will be if shear deformations are not taken into account. With thin plates, the margin for error is really not too high for not taking into consideration shear deformations. For Resner-Midland, the shear influence component is relatively high. We have a significant error when neglecting these shear forces. Like I said, higher value approach and more accurate shear forces will be taken into account with this theory. So now we can switch back to RFEM, and I can show you a little bit how different the results can be with these theories. So I'm going to switch back.
Hey, Alex, while you're switching back, we have a quick question.
Okay.
Can RFEM consider geometric nonlinearities and material nonlinearities? So geometric might be nonlinear nodal supports where it fails with uplift, for example, and then material nonlinearities such as a plastic analysis.
Okay, yeah, so short answer is that we can consider those. So nonlinearities like geometrically ones like support nonlinearities. So let's say let's say this concrete plate is sitting on the ground, and I don't want the support to support it if there's any uplift. So let's say I go into this support and I edit it, or I'll just create a new one. We can create nonlinearities. So if I don't want to take uplift in consideration, I could add a nonlinearity and have it fail if there's a negative support force. You can see we also have a lot of other list of options for your nonlinearity here that you can choose from, but we do have that for supports. With regards to a plastic analysis for nonlinear material, we do have that as well. So you can change your material type. If you go into, you can edit the material, but if you're creating a new material, if I go into create a new material, I can define the material constants here. And then with this material model, you can choose from different linear and nonlinear materials within this drop-down list here. And so we do have those options as well. And this is something that we take pride in having. So yeah, I don't know if you want to add.
Yeah, no, that's good. I think that it must also be known that RFEM includes geometric nonlinearities directly within the program. So nonlinear members is another one. You know, tension only, compression only, nodal supports, line supports. The other thing to consider with the material nonlinearities that Alex just showed is that does require the add-on module RF mat NL. So as a student, you have access to all add-on modules, but that's not a default option within the program. Only linear elastic materials are default. So with the add-on module, that will release those nonlinear material properties as well. So thank you.
Yep, you're welcome. Yeah, so yeah, member types is something I didn't go over yet. So yeah, I can briefly just go over that right now. So basically member types for this beam we have, this continuous beam, it's set to beam. If you're using or if you're designing a column, for example, there's no column type. You just want to set to beam, and the program will automatically be able to detect if it's a column based on the axial forces that are applied to the member. So yeah, so for beams and columns, you want to choose the beam type. But like Amy mentioned, for nonlinear members, we do have things like tension-only members where they will fail if there's any compression force. We also have cable members. We have a long list of different member types here. So yeah, nonlinear members there as well. Yeah, so we discussed basically the different plate theories between Resner-Mindlin and Kirchhoff, and then the beam theories between Bernoulli and Timoshenko. And yeah, so one considers basically, just to recap again, the Resner-Mindlin theory takes shear deformations into consideration, and the Kirchhoff theory does not take shear deformations into consideration. And these theories can be changed within our program under the calculation parameters here. So if I go there, and then I go under here, you can see under plate bending theory, we can choose between Mindlin and Kirchhoff. Right now, shear deformations are taken into consideration for our plates. We did deactivate shear stiffnesses for members. So let's say if we look at our surfaces here, right now we're looking at the moments. So if you look at these moments, our peak moments, we have about 11, 028, 026, 025. They change very slightly depending on the FE mesh here. And so let's say we go up to calculate and we change our plate theory here, just for example, just so you can see how these values will change. We can do that real quick. I'll click OK. So right now it's running, and it's running according to the Kirchhoff theory, so no shear deformations are taken into account. And we can just see how our results have changed. So they were changed very slightly. I wasn't really expecting too much of a change here. We have 11.08, 0.07, 0.06, and I wasn't expecting too much of a change because of our plates aren't really too thick. They're only 12 inches thick. Let's say maybe we changed the thickness of our plate here from 12 inches. I can do that easily just by double clicking on it. From 12 inches to 20 inches. We'll click OK, and it's going to ask me to recalculate. I can do that real quick. And again, with the Kirchhoff theory, with thick plates, it's not really a great theory for thick plates, because the thicker the plate gets, the more inaccurate your results will be if your shear deformations are not considered. So you can see here, our moment has increased. It's at 14 kips per feet. And so if I go up here to calculate and change this back and take shear deformations into consideration with the Mindlin theory, we'll see how much that value changes from 14. So that ran. And you can see now we changed from about 14 kips per feet to, it was about 14.08 to 13.9. So you can see how much of a difference that makes between those two theories, and how it changes depending on the thickness of your plate. So I'll change that back, and now we can move on to the next topic. But before I do that, I just have a couple questions to ask. So I will switch this back to the PowerPoint. And the question is, what happens if the shear stiffness is activated? So just to make sure everyone's clear on this, I would like, here are the options for the answers. First option is shear deformations are considered. A, B, increased accuracy in results, or C, the shear stiffness of elements is infinitely rigid. So again, you can type those in the chat and then we can go over the correct answer. All right, so I'm seeing mostly A, B, there's one C. So for this question, again, what happens if the shear stiffness is activated? And this is mostly pertaining to the beams. So if shear stiffness is activated, the correct answer is shear deformations are considered. So with shear stiffness, is basically, if it's activated, this is basically saying, okay, is the shear stiffness infinitely rigid or is it not? And like I mentioned in school, you assume shear stiffness for everything you calculate is infinitely rigid, and the shear deformations are not considered, but by default in RFEM, shear deformations are considered, and it's not assumed that it's completely infinitely rigid. So the correct answer is A for this one. And then the next question, or this is actually a true and false question. So it says the Kirchhoff plate theory does not consider shear deformation, and is this true or false? All right, so looks like a lot of you answered true. It's mostly true. I see a couple falses. So the correct answer for this one is true. So the Kirchhoff plate theory does not consider shear deformations, and the Reisner-Mindlin theory does consider shear deformation. So Kirchhoff is always the simpler option. Yeah. So I do see a question, what about B in the last question? So if I go back to the last question real quick. So B, increased accuracy in results. What happens if the shear stiffness is activated? So yeah, I mean, yeah, B, that one's also kind of correct as well. The accuracy in the results is increased. They could increase, they'll always increase with the shear stiffness is activated. So yeah, that could also be
Yeah, I wanted
correct as well.
to comment on B as well. I think that it could lead to increased accuracy, but I think this all depends on the thickness of your plate. Alex just showed an example of a thin plate where, regardless of which plate bending theory we chose, you don't see much difference in your results. Now, in the event that you have a thicker plate, when he increases to 20 inches, then yes, of course, considering shear deformation is going to lead to a more accurate analysis. So I still think, Alex, that you're correct with A being the answer all the time. B could be used as a correct answer in some cases, but there's other cases in the event of thin plates that either plate bending theory will give you almost the same answer. So it could be false in that sense.
Yeah, that's great clarification. Yeah, I think A is probably it's between whatever is the most correct. And yeah, like Amy said, if you have a thin plate, the results might not change that much or so. Yeah, great, yeah. Yeah, so we can go, and that was the last question for this section. So I think we can go back now again to RFEM, and we are going to start with modeling our Euler case 1 and stability analysis of our frame. So that was the end of the plate section. And so now we're going to get into stability. So to begin our stability model, we will just start with what we did last time to create a new model. And that is simply to go up here to new model. We'll click on that, and then our general data dialog box will pop up. And this model, I'm going to name it Euler case 1. And then I'm going to give it a description, stability, example, and everything else. I think we can just, keep the same. We can keep it as a 3D model. We can keep our combinations generated automatically. This isn't really necessary for, we're actually going to turn this off for this model. We don't need to generate our combinations automatically. We're just going to use load cases. And the standard, since it's not created, we can keep this the same for this example, and we can click OK. And once we click OK, our blank grid here will pop up, and then we can begin with creating our simple beam here. So first thing I'm going to do is go up here to new single member, and then I'm going to create a new member. I'm going to import it from our cross-section library. And I'm going to choose this member from our rolled cross sections, from our I sections based on a standard. And I'm simply just going to, for this example, use the AISC, and I'm going to choose the latest. And we're going to choose wide I sections with parallel flanges. And it's just going to be a W section, not really too important. The actual cross section, we're just going to choose 12 by 35. And then the material, you can see I have some that were carried over in this template. And I'm going to just keep it as steel A992. That works for this example. So I'm going to click OK. And I'm going to click OK again. And now I need to draw my member. I want to draw this member as a column. So this is going to be a column. And so I need it to be perpendicular to this grid surface here. So a couple ways I can go about doing this is, right now if I draw, I'm just going to be drawing in this XY plane along my grid. But if I choose this option here, length and direction, I can give it a length. This column is going to be 30 feet high. And then I can tell it to draw it perpendicular in the plus or in the positive direction, perpendicular to my work plane. And I can simply just draw this or place my column here. And now I have my column perpendicular to my plane drawn. Oops, didn't mean to click on that. Another thing I could have done was just change my work plane. So you have these buttons up here where I can change it from the XY work plane to the YZ work plane, to the XZ work plane. So I could have just done either of these and drawn it like that, but always different ways to do things with an RFM. It's always just personal preference, what you find more efficient. So now that we have our column drawn 30 feet high at the origin, we need to add a support to it. So I'm going to just zoom in, and I'm going to highlight my node down here at the origin, and then I'm going to click on new nodal support. You'll notice when I highlighted from left to right that I didn't select the member itself, I only selected the origin, and that's because when you draw from left to right, everything, or this box will only select things that are completely engulfed in it, not anything that it touches. But if I drew from right to left, then anything that touches this highlight box will be selected. So that's the difference between drawing from left to right and right to left. Definitely very helpful for selecting things. I'm going to go up here to new nodal support, and this nodal support is going to be a hinge support. So all 6 degrees of freedom are going to be fixed. So I'll click OK. And now you can see my rigid support down here has been added to my node at the base of my column here. And now the next thing I need to do is just create a new load case. So first thing you always need to do before you add any loading to your structure is to create a load case. Because again, like I said, each load case needs to have, or any type of loading needs to be assigned to a certain load case. You can't have loading without a load case. So we'll create our load case here. Again, not really too important with the name. I'm just gonna name it test. Action category, keep it dead. So then we can have our self-weight activated with dead, but for this example, I'm going to uncheck this active box. And so now our self-weight is not going to be taken into consideration for this example. So I'll click OK. And then I'm going to just simply create a new load. So this load is going to be a point load. I don't think I've shown those yet, but a point load would just be added to our node here. So to create a new nodal load, I'm just going to click on new nodal load. And then I'm going to tell the program what the magnitude and what component or direction this is going to be placed in. So I'm going to do it by component, and it's going to be a downward force, and I'm going to make this downward force 5 kips. And then I'm just going to have a lateral force of 2 kips in the x direction. We're not going to add any moments to this point load. We're just going to keep it as a regular point force here. And then I'm going to click OK. And then we can select the node that we would like to apply this to. And I just realized that I actually needed to have this point force facing downwards. I forgot to add the negative sign to it. So I can simply just double click on it, add a negative to it, and whoops, change that. I meant to change the one in the x direction. So let's go back, add a negative, and then delete this one. Not really too important. There we go. Now we have our downward force on our column here. And now that we have our loading applied for the column, I would like to get into something very important. So we have our loading, we have our column, we have our support here, we got our load case. Something important to go over, you'll see once I click calculate, I'm going to hit calculate. I basically just hit this button up here called show results for this load case. And when I click on that, it asked me if I wanted to calculate the results since they weren't ran yet. So now we have basically our global deformations for our column here. So if I get a elevation view of our column, you can see we have our deformation, our maximum deformation, which is 3.782 inches. I can also check out the internal forces of our column. I can take a look at the moment along the length. So you'll see the maximum moment, it's at the bottom. It's of negative 60 kip feet. And now that we have our deformation and our internal forces looked at, so again, 60 kip feet, our global deformation was 3.782 inches. I need to show you how this linear or first order calculation differs from a second order calculation. So what does that mean exactly? Well, for load cases in RFM, if I go to my load case here, I can go to calculation parameters, and load cases in RFM by default are ran by a geometrically linear analysis method. So by default, it's a linear analysis. And so if I change this to a second, I can change this to a second order analysis. Load combinations, however, are ran by default by a second order analysis, which takes into account little p delta and big P delta. And basically, this will give you more accurate results, more real world accurate results with a second order analysis. And again, by default, load combinations are run in a second order analysis. So I'm just going to delete this load case real quick. And basically the difference between a first order, so a first order analysis sets the equilibrium of the beam based on the undeformed system, and a second order analysis sets the equilibrium based on the deformed system. So I can show that. So if we change this to a second order analysis and I click OK, we can rerun our results. And I'll rerun the results, and you should see that our bending moment that the deformation and bending moment has increased. So you can see now with taking a little and big P delta into account, we have a larger deformation at 3.905 inches. And then if I turn on my member internal forces, we went from 60 kip feet to 61.6 kip feet. And this is because, again, of the P delta effect. So since the deformation increased, basically, our deformation increased, the applied axial load here has increased because, well, the applied axial load has an increased moment arm, which then in turn increases the maximum moment that we have down here. So just keep in mind that you will get different results when switching between, if you have the exact same thing modeled in a load case or load combination, you need to keep in mind the defaults that are set. So again, a load combination by default runs a linear analysis, and a load combination runs a second order analysis by default. Those can be changed, but just wanted to point that out. Another note that I already mentioned, again, columns, members in RFEM are determined to be a beam or column based on how the loads are applied. In this case, we have a column because of the axial force that's applied here. So then now I'd like to change the loading on here. So to get into a different example, I'm going to change the load here from 5 kips to 100 pounds. So I'll make that 100 pounds negative. Oops, actually, there we go. And then I'm going to make this 0. And now we're going to get into the atom module RF stability. And so I'm going to change that. And so basically, to go over atom modules again, atom modules for an RFM are basically just separate dialog boxes, but they are mostly used for design. So for example, if I go up here to atom modules, we have them organized by material. So we have RF timber for timber design. We have the RF timber CSA for Canada. Also the aluminum, we have the ADM, RF aluminum ADM atom module for aluminum design. Concrete, we have RF concrete surfaces for designing reinforcement for both columns and beams. We have RF concrete surfaces, and also RF steel for RF steel surfaces, members, and then we have separate modules for different standards such as the EC3, the ASC, the CSA. So we have lots of different design modules along with dynamic modules. We also have our stability module, which we'll get into, and then a couple others. So to open an add-on module, it's as simple as just clicking on it. And once it opens, you'll see it's basically just a dialog box. And the modules take all of the information from RFEM from your model, so there's no need to redefine anything in the add-on modules. You don't need to redefine cross sections or materials or anything like that. You can simply just open them up. And this is the RF stability add-on module. So just to go into a little bit of a background, the RF stability add-on module uses the help of eigenvalues and different eigenforms to perform a stability analysis. So Euler was a mathematician who came up with different cases to show the critical load factors as well as critical loads and lengths. And this is something that every stability analysis does. And so it is important that we go through the options here before we run our calculation and find out if our structure is stable and can handle the loading applied to it. So the first thing I want to do is activate the division of straight members. So I can do that right here. Right now it's already activated by default. I can also hit this edit button, and then I can go down here to minimum number of member divisions. Right now it's 2. I want to increase this to 10 just for more accuracy. And then I can simply just hit calculate. So my calculation will run. And once that's done running, we will get our results here. So we had our input data, and now we have our results. And right now we're showing our critical load factors. And so basically these critical load factors are the amount, or this critical load factor here would be the amount you would have to multiply the loads by in order to get an unstable system. So right now it's at 135.247 for this first eigenvalue number or eigenmode, and I would have to multiply the loading on my beam right now by 135 times to basically get an unstable structure. It can also be looked at as the total percent of the loads your structure can take. And then we have our effective lengths in this next table here, table 2.2. So we can get a better look, or we have our effective lengths, and we can also take a look at these effective lengths or our results graphically. If I go down here and hit graphics. So right now I'm looking at my first eigenmode 1. I can also make this yellow line here, the deformation of my column, colored. So if I go to display, and then under display, I scroll down here to results, and then I go to deformations and members, and then I go down here to cross sections colored. I can turn that on, and now I can get a better look at the eigenvalue, and it's color coded and everything. So we can get a better look at exactly where on this column those results are taking place. I can go back here to the tab in here, factors, in my panel, and I can simply scroll through my different eigenmodes. So you can see what those look like. We're mostly focused on eigenmode 1, and I think it's clear that the column will first be unstable in its weak axes. So if we're looking at it, if anything, the weak axes will be the most unstable, and basically the weak axis for this column is in the y direction about the local z axis, and we can see that if I double click on it. So we have our z axis and our y axis, and we're going to have our weak axis bending about the z axis here. So, and another easy way to look at this is if I go to my info about cross section. I can then scroll down here to my modulus of elasticity, or to my moment of inertia. Here it is. So I can see my moment of inertia about the y-axis and z-axis, and you can see about the z-axis, my moment of inertia is a lot less. So another great way to see which axis is the weak axis. So we can close that. And yeah, so that's basically the reason why the column buckles about the z-axis. So now we can go back easily to RF stability by just going to my project navigator here, and you can see that out of all of my atom modules here, that RF stability has thicker text to it telling me that I have results or have data saved in it. Something else, so you can see we have our list of atom modules. Something else you can do is you can right click on any of them and you can set them as a favorite. So they're all under your favorites folder here. Another easy way to keep track of the ones you use the most. So I'll just simply double click on RF stability. And then we can take another look at our effective lengths here. So we have our effective length factors and our effective lengths depending on which eigenmode we're looking at, and then our critical load. And we can also show what it looks like when the structure is unstable. So this would be due to your loading being too high. So let's say I'll click OK, and I'll go back to, I can go up here to my dropdown and go back to my load case 1, and I can change my loading real quick to something that would make this column unstable. So I will turn this to, let's say, negative 14 kips, and I'll click OK. And right now I have my, let me just make sure that my method of analysis is linear. So right now it's set to second order. Let's see what happens if I have it set to second order with too high of a load. If I go into RF stability, and then when I'm in the RF stability, I want to make sure my model is stable, so I'll click OK. And run the calculation, and it's giving me an error message basically saying LC results are not available, and this is because my model is unstable. So what I need to do is go to load cases and combinations, and basically when a model is unstable, you can't get RF stability results when it's running according to a second order analysis. We need to change this to a geometrically linear analysis, so I'll click OK. Then I'll go back into RF stability, and we should be able to now run our calculation and find out how much our loading needs to decrease, or also how much or what we need to change about our model. So you can see right now we went from 135 for a critical load factor down to 0.96, which is less than 1, which is not good. So if you get a critical load factor less than 1, this basically is saying that your model can't handle 100% of the loading. It can only handle, for this example, around 0.96 or 96% of the loading applied to it. So that's another way to tell if your model is unstable, is if this critical load factor is below 1. So I'll click OK. And what I would have to do to make this model stable is either increase the size of my cross-section or change my cross-section of material or change my loading, and there's a couple other ways too as well. And yeah, so that's basically how to use RF stability to take a look at different eigenmodes, critical load factors, and check the stability of your model. I'd like to jump back to the PowerPoint again for another question. And this one is another true and false. So the statement is the critical load factor specifies which factor can be used to increase the stiffness until the structural system fails. And you have the two options, true or false. Looks like now is also a good time to take a quick 5-minute break. So I think we'll take a 5-minute break and then we'll come back and go over what the correct answer is for this statement. So we'll come back here at 3:07. All right, so let's go over the answer for this question. Again, the critical load factor specifies which factor can be used to increase the stiffness until the structural system fails, and that is true. Or sorry, that's false. Oh, so that's false, and the critical load factor basically specifies which factor can be used to increase the loading until the structural system fails. So looks like everyone mostly got that one correct, and so that's great. So now we can move on to back to RFEM. And so we're done with the Euler case one example. And so now we can move on to creating the moment frame. And to do this, it would be pretty easy. Oops. So like I said, we can move back to RFEM. And now that we are done with our column here, we can basically just change it or use it to create our moment frame. So what I'm going to do is change the force back to a normal force, or back to the force it was before where we didn't have an instability. So I'm going to change it back to -5 kips. And then we can add our lateral force back in. And I'll click OK. And then basically we're just going to use this column as our first member for our moment frame here. So I'm just going to take this and hold Control and copy it over. Oop. Let's try that again. Move and copy it. And now I'm just going to basically do that one more time. And I basically just want my column, the columns of my moment frame to be 10 feet apart. And what I can do to change my height of my two columns here pretty quickly is I can just drag from left to right, and then I can double click on the nodes here and edit them. And if one of the coordinates for your nodes is the same as the other node, you'll see that you can change it. So the coordinate for these two nodes that I highlighted, 4 and 6, have the same z coordinate. So I'm going to change this from 30 feet to 10 feet, and it'll shrink down both my columns here to 10 feet. And now I just need to basically add in my beam to connect my two columns here. So I'll go up here to new single member. And I'm going to create a new member from the cross-section library. And this is just going to be another I section. And then I'm going to scroll down. This section is going to be an 8 by 15. And I'm going to keep the same material. Click OK. Click OK again. And then I'm going to simply just draw this beam and connect both of my columns. So I'll right click, and now I have my moment frame basically. I'm going to take out both of the lateral forces here by just holding Control and selecting both of my loads and deleting my lateral force. I'm gonna hit OK. So now we basically just have our moment frame here. And what I can do is run my calculation. And once that runs, we should see we can take a look at our normal forces. Right now we don't have any moments about the y-axis. And we can take a look at our global deformations as well. Really not any right now on our moment frame. So what we could do is increase the loading. But also we could just add a uniform load to it. So I could go up here to new member load. And I can go to force, and then I can go to uniform and have it in the global z direction. And then I can apply something like -3 kips per feet. Hit OK. And I can just apply that to our beam here and rerun our calculation. And we should see some more interesting results. So you can see it's a little tough because our deformation of our column here is a little higher than our moment frame here. So if I went to view, visibilities, and did this by member cross section, you can see we have a little bit of a better view of our deformations here, of our cross section. We can also get a better view of our internal forces or our moment diagram on our beam here. And we could also just turn off our views and then again see the results on the rest of our frame here. And we can also then go up here and scroll down and choose our RF stability case here, and then we can run our RF stability results. And now we can take a look at our results for our moment frame here. What I can do is just highlight this, and then I can make a visibility by selected objects, and I can simply just keep my moment frame. I can right click and turn off show hidden objects in the background, and then I can go over here to filter, and I can specifically just show the results of the moment frame filtered. And now we should be able to get more of better looking results for our eigenvalue here. So if we go into general data, and then let's go back to turn off our cancel this visibility, and we will have this set to all. And then if we deleted our column here, and then went back into our stability, and ran the calculation, now we should see our critical load factors for our moment frame here. So 4, so pretty good for the first mode. Now we can get a better look since our column is not taking up the results there. So we can scroll through here and see our different eigenmodes for our frame here. You can see the first eigenmode. Right now our frame is bending out of plane for our first, and you can see our other 4 there by scrolling through here. We can also increase the factor here to get a better idea of what these look like. And then let's say for our frame, we really don't want it to deform out of our plane here. So what I could do is simply highlight both of my 2 nodes here. So I can hold Control and highlight them, and I can add a nodal support to them. And this specific node support, I just want to have it keep my frame in the XZ plane. So I'm going to allow it to rotate about all axes or all degrees of freedom for rotation. And then I'm going to allow it to simply just not be able to move out of in the Y direction. So it can move in the X and Z direction. So we can click OK. And this will basically allow it to move up and down and left and right, just not forward and back, and rotate. So now we can now see what this looks like, and you'll see that it'll keep it in plane, and we should have a lower critical load factor, or higher critical load factor. So if we go back into our stability, you can see that my first eigenmode looks a little bit better. And now we have a higher critical load factor of 21. So we increase the stability of our moment frame here. And that is the end of the stability example. And I wanted to leave this section open for questions and discussion. So we're basically going to move on to the concrete example. But before that, like I said, if you have any questions or any subject you want to go over or want me to go back over, something that you were confused about, you can put that in the chat and we can go over it, or I can answer any questions before we move on to the concrete example. So while you're typing or asking the question, I'll just simply move on to the concrete model, but I will stop and we can discuss anything or go back over anything if something comes up. So let's see. So yeah, so it looks like the other question was training module be available for future reference. Not sure about that question. It seems so. The
I
R
think this
stability
is just referring to the training today being
okay.
recorded.
Oh, okay. All right. Yep. So yeah, this training is recorded and will be accessible to you guys afterwards. Not right afterwards, but within a day or two. So yeah. So yeah, so let's move on to, I'll just move on and keep going over the concrete model, but if anything pops up, we can go over that then. So again, create a new model. We can go up here to new model. And this new model will be the concrete model. And we can give it a description and we'll keep it 3D. And then for the standard, we're gonna select the ASCE 716. And for this one, we are going to create combinations automatically. So we'll get to see how that works. And we're gonna keep the positive orientation of our global Z axes upward. So all of this looks good. We can click OK. And yep, and so now we have our blank model here. And the first thing we want to do to create our model is to first create the floor. So we want to create our floor slab of our concrete model here. And to do this, we are going to use the new rectangular surface tool and then choose our material. So we want to go to import new material from material library. And we're going to go under concrete and then standard. So we'll just, for this example, use the ACI and the most recent standard, 4,000 PSI concrete. And we'll keep this all the same, 8-inch thickness. Then we'll click OK. And basically the floor of the structure is going to be 46 inches or 46 feet by 40 feet. And one thing I'd like to point out, well actually, so our grid is the correct size, it's 50 by 50. So no need to worry about that. So we'll go up here to 46 by 40. And now we have our floor slab down. And now the next thing we want to do is basically create the columns that are going to be supporting our ceiling. So I'm going to go over here on the very left-hand side, and I'm going to select my node here on the origin. And then I'm going to go up to my move/copy tool. And I'm going to make one copy of that node. And then I'm going to move it 2 feet in the X direction and 2 feet in the Y direction. And I'm going to click OK. And now I have my first node placed here, which will act as my base for my column. And now I just want to do basically the same thing, just create two other nodes. And I'm going to again use the move/and/or copy tool and make 2 copies of that. But I'm going to only have it be displaced in the X direction, 16 feet. So I'll click OK. And now my corner node over here, I'm going to also make a copy of, but this time I'm just going to hold Control and move it. Oops. Hold Control and then move it. There we go, make a copy of it. So now we have our first row of nodes here. And now I'm going to basically make a copy of this row of nodes. So to do that, I can simply rotate my model here and then hold down Alt. Oops. I can hold down Alt and then that allows me to highlight over top of the surface here, allowing me to select my row of columns here. And then I'm going to use the move/and/or copy tool and move that 13 feet in the Y direction. But I'm only going to make, so 2 copies. Then I can click OK. And now I have my slab here with my rows of nodes. Now I'm going to turn on, so I can also turn on and show the numbering of my elements here in my work window by just right-clicking and going to show numbering. So now we can see the number of our nodes and also the number of our surface and lines here. And then we need to divide our line. So we can divide our line, our left-hand side line here to create our boundaries for our walls. So I can divide line, and I can do that graphically. And I want to divide my line right here. And then I want to do the same thing for this line up here, right about at here, to line up with my rows of nodes here. So I'll click OK. And now we have our lines here divided. and I can now create a semicircle surface. So this structure is going to have a spiral staircase on the right hand side of it here, and so I can create a different shape surface here. And to do that, if I go up here to my new rectangular surface tool, I can hit this little arrow here and I can get a nice drop down, and you'll see we have a bunch of different shapes here. So we have rectangle, circle, semicircle, ellipse, and polygon if you want that. And then also you can draw out your lines anywhere on the grid and then select the boundary lines and create a different shaped surface like that. So I'll select semicircle, and then everything here is defined correctly, so I'll click OK. And now I'm going to just choose the center of my semicircle, and that's going to be 7 feet. Well, it has a radius of 7 feet, so I'm going to choose it 7 feet from that top corner. So that should be at 33. Then I can choose that center and click a second time on the corner node there. And now I have my semicircle surface drawn here. So that's all good. And now we can create our ceiling slab. So basically the geometry of the ceiling slab for this structure is going to be the same. And it's just going to have a thickness of 12 feet and a clear height of 11 feet between the two slabs. So basically what I can do is highlight my slab here, and then I can move/copy it. And I'm just going to make one copy of it, and I'm going to have it be displaced 11.83 feet into the Z direction. To take into account the thickness of the two slabs, I need a clear height of 11 feet between the two. So the 0.83 feet comes from the thicknesses divided by 2 and added together. So we'll click OK. And now we have our two slabs here. And something I did want to point out is that the center line of any slab in RFM is in between the thickness of the surface. And what I mean by that is if I go over here to display, right now the thickness of the slab is not being rendered, it's just being rendered as a 2D element right now. But if I go down here to display, and then I go to rendering, and I go to model, or I'm sorry, if I go, so model, and then I go to solid model, and then I go to surfaces. If I choose filled with thickness, you can see now we actually have the thickness of our slab here, and the center line of the surface is lying halfway between the thickness. So that's why that's why I added 0.83 feet to the height to make sure that the actual distance between these two slabs is 11 feet. So I'm going to turn that rendering back to just filled. And now I'm going to turn this into a different view. So right now I can turn this into an isometric view, which is very handy. And then I can turn this into a perspective view if I like. And the nice part about a perspective view is if we are looking at the model in the reverse Z direction, I can go to perspective view, and now I can get a look at both the ceiling slab and the floor slab. So now the next thing I want to do is create my wall, or the next thing I want to do is divide this line here, line 10. So what I can do, or I'm sorry, I want to divide line 16 here so I can get a center point for my spiral staircase here. So I'm going to double click and select line 16. And then I'm going to right click and go to divide line and then go to distance. And right now I have line 10 selected since it's lying over top of 16. So I'm just going to type in 16 manually. And I want to divide this line a distance of 7 feet from the start. So I get a perfect node right here in the center. So I'll click OK. And now I have my node here. And what I want to do is make sure that this line 10 here is split at this node here. So when this line comes into contact with this line 10 here, I want to have that split. So what I can do is use my tool up here called Connect Lines or Members. And then I can simply highlight node 40 here. And now you can see that this line 10 is separated, and it was separated into lines lines 17 and 18 here. And what this will allow me to do is now I can delete lines 16, 17, and 18 here. And I'll do that once I can delete the surface, because I want to join these two surfaces together, the semicircle and the rectangle. And now I can delete lines 16, 17, and 18. And another way to do this, other than graphically, would be to go into the project manager or navigator and go to lines. And then if I select lines 16, 17, and 18, you can see that the project navigator is synced up with the graphics or with the work window. So if I click them, you can see, I can see exactly where these lines are that I'm selecting over here. So what I can do is just hold shift and highlight and select all of these lines and hit delete. And now I just have the boundary line of my ceiling slab here. And what's nice about that is now I can simply just turn this boundary line into a surface by going up here to the new surface button and then hitting this drop down, going to select boundary lines, and then I can choose my parameters here. I'll change this 8 inches to 12 inches for the ceiling slab, click OK. And now this is asking me select your boundary lines. And so I'll do that graphically. And now we have our one surface here that's, instead of two surfaces, just one rectangle or one large surface. So I'm going to take this out of perspective view, go into isometric. And now the next thing I want to do is add openings, or add an opening to our top ceiling slab here. And adding openings in RFEM is really easy. We have a tool for it, and it automatically integrates the opening into the surface. So what I can do is go up here to the opening tool, and this opening is going to be a circular opening. And so all I need to do really is just select the center point, and now you can see why we divided that line. So I have my center point here. I can select that, and the opening is going to have a radius of 6 feet. So I can just go over in this window over here, type in 6 feet, hit enter. And now I have my circular opening, and that will act as the opening for the spiral staircase. Now the next thing I want to do is add the walls to our model here. So I'm going to rotate this so the right hand side is facing the front here. And basically, to add in the walls here, we just want to define our boundary lines. So really easy. I'm simply just going to divide some of these lines here so we can get some intersection points to draw our lines. So this first line is going to be at 7 feet away from node 20 here. So we actually don't need to divide the lines. We can simply just go up here to new line. And then we can just click, and from 7 feet from 20 here, we can go all the way down to 4619. I can click, and then you can see that I want this line to be perpendicular to my ceiling slab. So you can see there's going to be a nice symbol here telling me that I can click on this point here and it'll be perpendicular, allowing me to draw that perpendicularly. And now we have a line, which will act as a boundary line to our wall that we're going to draw out here. So now the next thing I need to do is just connect, or actually we're going to draw one more line in the back here. And this one is going to be 12 feet away from our staircase here. So I'm going to draw that at 34, 46. Oops. There we go. We can snap to our point there and right click. And now we have two lines here. And now all we have to do is connect some more nodes here. So nodes 20 and 40 will be connected. And then 3 and 23. 18 and 38. 4 and 20. And then last but not least, 17 and 37. So now that we have all of our lines for our walls here, I can right click and exit out of that tool. And all we have to do now is use the, well, first before we make any of our walls, we need to use the connect line / members tool and simply just highlight our whole model. And that will split up any intersections with the lines, creating new lines. And now we can use the tool select boundary lines. And with this, I can simply just select the boundary lines to create my surface. These walls are going to be 8 inches thick. And then our concrete is going to be the same, 4,000 PSI. So we'll click OK. And now I can simply just select the boundary lines. So make sure that you select the adjacent ones so they're connected. So you can't select any lines that are not connected to the line you first selected. So make sure they're in a chain. Now we just got to do one more. And now we have almost all of our walls created. The last wall we still need to create is this curved wall here for our staircase. And this can't be done with any of these surfaces because it's out of plane. It's not located in one single plane. So what we have to do is go over here to this drop down here for curved surfaces. So I can go over here to quadrangle, the quadrangle tool, click on it. It's going to be 8 inches, same material. I'll click OK, and now I can simply select the boundary lines for this curved surface. And now we have our curved surface for our spiral staircase. Next thing we're going to do is create our columns. And one other thing I did forget to do is we did have one more wall to create. We do have one load bearing wall right in the center here that connects nodes 18, 38, 34, and 14. And to create this wall, we can use the rectangular surface tool, but we do need to make sure that our work plane is in this plane here. So what I need to do is change this to the YZ plane. And now my work plane is in the YZ plane, but I need to get it right here at node 18. So what I can do is change the origin of my work plane. And to do that, I can go up here to set origin of grid/work plane. And I can click on any of these nodes. I'm going to click on 18. So now our work plane is in the plane of where our load-bearing wall is going to go, connecting all 4 of these nodes. And now I can go up here to rectangle. I can hit OK. And now I can just simply select the 2 points that are going to make up my load-bearing wall. So now we have that created. I'm going to turn this back into my XY plane. And now we just need to create the columns. So lots of different ways to do this. I know we went over how to create the columns just using this button to create a new single member. A different way to do this would be to create a new line. So we could create a new line and connect these 2 nodes here, 5 and 25. And this is useful. Let's say you just have this line already created and you want to turn it into a member. Well, we can double click, or you can double click on any line here. And within the edit line window here, there's a tab called member. And if I go to member and then I go to available, this will let me create a beam from the line or a column or any member you'd like, basically. And I can go to import from cross-section library. And then I can tell it what cross-section I would like. So parametric massive, since this will be a concrete column. And then the base of this concrete column is going to be 14 inches by 14 inches. Or yeah, base will be 14 inches and the height will be 14 inches. So then I'll click OK. And we can keep the material the same. And then if I click OK through all of these dialog boxes, you'll see my line has now turned into a concrete column. And so now we can do this for the rest of our model. I mean, we don't have to create the line and connect these. What we can do is use our workflow of selecting the member, holding control, and dragging right at the node here. And then we can create the rest of our columns doing this. Oops, Control Z. Let's try that again. And then we will have our row of columns. There we go. Now that we have a row of columns, we can simply copy them again, and then we don't have to worry about creating them again. So one thing I would just like to show is if we go to our table, for example, if I wanted to see what kind of members I have in my model through my table here. So I can expand this table, and then I can go to, right now I'm under material, so I can see which material I have in each of or throughout my model. I can also go to the tab members here, and now I can see I have all 4 of my members. There are beams, member types. I can see the type of cross section they're made of, and I can select them in the table here individually and change things about them if I'd like to. So I could change something like the member type here. So the tables are pretty powerful for quickly, or if you have a large model and you need to quickly and easily just see the different model data and change it very quickly, this is an easy way to do that. So if I want to select something in my model, I can do it graphically, or if I have a lot of them in a lot of different places and they're very hard to find, a lot of different of these, maybe they're smaller elements within your model, you can go up here to this button called Special Select. This is another tool we have. And I can simply tell the program, okay, I want to select members. And I want to select all members, or not all members. I want to select only members that have a cross section of 14 by 14. And then I can click OK. And now the program will select all of the cross sections with 14 by 14. And that makes it easy if you have a large model with lots of different smaller elements maybe that are hard to select. So then we can just simply take this, hold Control, and then drag and try that again. There we go. So now we have our copy of our columns. And the next thing we need to do is just add one more column to connect nodes 15 and 35 here. And then we'll be done creating our columns. There we go. All right. Okay, so we're gonna let that one go and simply just draw that one out. There we go. And now we have our columns created. And now we just need to create our last element, which will be our downstand beam. And that will connect from 37 to our load bearing wall to our column over here. I can simply just delete node 33 here as we don't need it. And I can go up here to create my new single member. And then I can create my new single member. So this one will be a cross section of 12 inches by 12 inches. So I'll go to my cross section library. And then again, this will be a parametric rectangular section. And it'll be 12 inches by 12 inches. And this one will be a different member type. So this is going to be our downstand beam, and it's going to be dropped down right flush with our surface or our ceiling here. So what I want to do is change this member type to a rib element. And so what a rib element will be also have integrated widths with it. So what I can do now is changing this to a rib element. I get this edit member type button here. And you can see what this rib element will look like. It's going to be integrated with our ceiling, with our slab, and it's going to be dropped down to be flush with it. So I want it to be on the positive Z side or local Z axis side of our surface. And you can see what the two differences are in this graphic here between those options. So this is just changing the alignment and position of it. And then we need to tell the program what the width, our integration widths are going to be for side 1 and side 2. I'm just going to make the width L/8 for both sides. And then I'm going to click OK. click OK again. And now I just need to draw out where my beam element is going to go. Oops. All right, so first we're going to draw the line connecting 37 to 34 and then 34 to 35. And then I'm going to select both of those lines, double click them to edit them, and check on the member available option here. And again, we're going to choose our rib, which we already have defined. Well, choose our section. We need to define our rib. We'll edit the member type again. And all of this is set OK, so we'll hit OK again, and then again. And now we have our rib element created. And you can see that it's dropped down below the surface. And so everything there is defined correctly. And now we need to create an opening in the back of our model here. So to do this, I'm going to change the work plane again to the XZ plane, or XZ plane. And then I'm going to change again the origin of my work plane. And now I can simply draw on this surface the opening. And it's going to be a rectangular window basically. And it's going to be 9 feet wide and 5 feet high. So we'll go down here and we'll go to the coordinates 3, 0, 5. And it's easier to see the grid points if I change this into a wireframe view. And then we'll draw our opening here. And this one will be, there we go. So now if I change this rendering back, now we can see we have our opening there. And now we basically have all of our, model created, and the next thing we need to do is add some supports to it. So I'll change my work plane again, and the next thing we need to do is add in some line supports. So we'll go up to our line support tool here, and we can add in our hinge line supports here. And with these, I'm going to create a new type. So I'll just turn off the translation in the X and Y and release those, because these supports, we're pretending that this structure is sitting against another structure adjacent to it. So it's able to be supported in that way. So it's only being supported in the Z direction. And so now we have our supports there. And then we can add in our surface supports by just double clicking on our surface and hitting edit, or just going to the edit. And then we can go to the tab support/eccentricity and then hit available. And for our surface support, there's only going to be spring constants. And for the X and Y, we're going to have a spring constant of 640 kip per cubic feet. for our X, Y, and Z. And that is going to be our foundation modulus for the gravel that's underneath our structure here. And then for the shear, we'll have spring constants of 32 kip per feet and 32 kip per feet. And then we're also going to have a nonlinearity. So if there's failure, there will be failure if negative contact stress is in the local Z direction. So if any uplift happens, then these supports will fail. And we'll click OK. And now you can see our nonlinear supports with only spring constants are applied. And you can tell they're nonlinear easily graphically by seeing that they're blue and green means they are linear supports. So that basically concludes what we have time for with this model today. So I'm going to switch back to the PowerPoint. And just to conclude, if anybody has any questions, please feel free to ask them. I don't think there's any more questions after, yep, no more questions after the Euler case example. So yeah, we'll just leave this last minute or two for questions if anybody has any extras. I can try to quickly answer those and clarify anything. I see a question. So how do we get the spring constants? So the spring constants, I'll switch back real quick to RFEM. The spring constants, basically, to get those is you release any direction, and once you can see right now it's grayed out because it's fully fixed, but if I unrelease this, then I now have a spring constant that I can add. So as long as it's not fully fixed, you can get a spring constant.
And I'd also like to add that this is information that the engineer might get from the geotech report. This is not something that we can necessarily give advice on. It depends on your soil parameters. And again, most likely this comes from the geotechnical report where they give you a soil spring stiffness.
Yep. Yeah, thanks for that clarification, Amy. Yeah, that was mostly for example purposes. So yeah. So I'll hop back. And if there aren't any more questions, well, if there are any more questions, you can email us and I'll go through our contact email and everything. So yeah, I don't think there doesn't look like there's any more questions. So basically I'll start concluding. So we do have some free online services on our website. I just wanted to point out, we have our GeoZone tool. We also have our cross-section properties library there on our website, which is handy. We have FAQ and knowledge base articles that are very handy for new users and beginners. I use that a lot as well, so it's very helpful to find things on there and help you with any aspect that you're having a question about with modeling and the knowledge base articles or any frequently asked questions you have. We also have a section on our website for models to download, so you can always take a look at those and download some models and get a look at some different designs there. We also have our YouTube channel that includes webinars and short tutorial videos, also very helpful for new users or even experienced users if you're just looking for different things to get into, different designs and things like that. We also have our web shop with prices and then our trial license as well on our website. And the most important feature is we offer free support via email and chat. So you will find our email down here at the bottom, info-us@dlubal.com. If you have any issues with any of your models or if you have any questions, please feel free to send them in or ask us questions through this email. We'll be gladly to answer them. We also have our phone number as well down here, so give us a call. And again, feel free to check out our website with our videos, recorded webinars. We have new newsletters on there, along with the other events and conferences we give, and also our knowledge base articles, which I find very helpful as well. So yeah, I would just like to thank everyone for attending. And one last thing, there will be an evaluation that we give after this webinar is ended. So please fill that out and give us your feedback on how you think the training was. If we need to fix anything or improve on anything, that would be greatly appreciated. Thank you very much for attending, and I hope everyone has a good rest of their day and a safe week. So thank you again, and have a good day. Bye.